In this video, we're going to be talking about how to solve some exponential and logarithmic application problems. And when we do that, we're going to be looking at some typical mathematical models or graphs of some of these applications and try and match them. So on this first page, we got about 6 different typical mathematical models of exponential or log graphs or equations here. And these first two, these are the standard exponential growth with its equation and exponential decay. Notice that negative exponent making it decay. We got a Gaussian model used a lot for statistics, a logistic growth model, kind of a crazy little exponential graph there. And then we got some log models. Typically we have a natural log or the common log, log base 10, or log base e. So we'll come back to that page as we are solving some applications. So a lot of word problems here. Some of them certainly have more steps than others. In this first one, we have quite a few steps here. We have a research experiment in a population of fruit flies. We know that after 2 days there's 100 flies, and after 4 days there are 300 flies. So we're going to use that to set up 2 different equations here. One equation is going to represent after 2 days we have 100 flies. We don't know what our initial population was, and we don't know the rate at which they're increasing. So 2 unknown variables there. If we can set up a second equation, we're going to be able to use a substitution technique and solve for one of those missing variables. So we'll set up our second equation representing after 4 days we have 300 flies. So again, missing our initial population and the rate at which they're increasing. So what we're going to do is we're going to pick one of these equations. It doesn't matter which one. I'm going to choose the one on the left though, and I'm going to solve for p. I'm going to get an expression that could be represented using r, so that when I substitute it into my second equation, the only variable I'm missing is r. So dividing both sides by e to the 2r gives us our p value. I can then take that quotient and plug it into the p spot in our second equation. That allows me to simplify my e to the r powers. I have e to the 4r on top and e to the 2r on the bottom. So dividing terms that have an exponent means that I just subtract the exponents. So I'm left with e to the 2r on top. So now I have 100 times e to the 2r. I can divide by 100. That leaves me with 3 equals e to the 2r. I'm going to undo this exponential equation of e by using its inverse, the natural log. So if I natural log both sides, I have the natural log of 3 on the left and just 2r, because the natural log will cancel that e and drop that exponent down. Now one more step to solve for r. I divide by 2, and so r will be represented by this quotient or decimal value if you want to do that instead. Now that we know what r is, I can plug that into the p equation and I can figure out what our initial population was. So plugging the r in to our p equation, I chose to leave it in this form because there's a lot of canceling that's going to happen. It's going to simplify nicely. However, sometimes you may want to just use that decimal equivalent instead. I'm actually going to use that in a future step here. But watch what happens when I plug this quotient into the r spot. I have 2 multiplied and divided, so the 2's are going to cancel. That leaves e to the natural log of 3, and e raised to a natural log power is going to cancel itself and it's going to drop that 3 down. So our p value is 100 divided by 3, or in other words 33.33333. So now I have all the values I need to plug into my equation representing continuous growth. So I'm going to plug my 100 thirds into the p spot. I'm going to plug the natural log of 3 divided by 2 into the r spot. And we're going to solve for the number of flies after 5 days. So I'm going to substitute 5 to the t spot. Now your calculator can do all this for you, but it's quite complicated to type it all in, so it may be easier in this case to use some decimal values and approximate. So instead of 100 thirds, use 33.3. And instead of the natural log of 3 divided by 2, use its decimal value, 0.549. That's a little bit easier to type into your calculator and get a result. And it should tell you it's about 518 flies. Now you can also take your equation and you can graph it, and you could substitute that 5 for just x, or an input variable, and then you could find the number of fruit flies at any number of days now that we have the equation for it. So a lot of steps there in that first one. The next one is very similar, just using bacteria instead of flies, so another opportunity for you to practice those steps. You can pause the video and try that one out on your own. I'm going to walk through this one a little bit more quickly than that last time. Again, we got our two equations here. We got 100 bacteria after an hour, represented by this equation, and 200 bacteria after 2 hours, represented by this equation. This is actually not mathematically required, since we are just growing or doubling every hour, but we'll do the math just to make sure that that's true. So our first step was to get a p expression, so divide by e to the r. Plug that into the p spot in your second equation, which allows you to solve for r. We're going to simplify e to the 2r over e to the r, that's just e to the r. Divide by 100, natural log both sides, and our r value is the natural log of 2. So now we can plug that in and figure out what our p value is over here. It's going to be 100 divided by e to the r. Well, e to the natural log of 2 is just 2. So 100 divided by 2 is 50. So now we know our initial population. We're going to find the bacteria after 3 hours. We know that the rate it's increasing is represented by the natural log of 2. So plug that into your calculator or solve it algebraically here. Either way, you should get 400 bacteria. So that's population growth. So if we go back to that front page, we knew that things were growing exponentially and continuously. So population growth is definitely an application of that growth model. On to our next application. Carbon dating is one way that we can use exponential functions. We got organic material that is decomposing at an exponential rate. It's going to be exponentially decaying, and we can recognize that in our function because of the negative exponent. So we know that as our time is increasing, the amount of dead organic material is decreasing or approaching 0. So if we plug this r given to us in this section here, 1 over 10 to the 13th power, set that equal to the right side given over here, we can solve for t and figure out or estimate the age of a fossil using this equation. First thing is to get rid of this division of 10 to the 12th. So we multiply both sides by 10 to the 12th. 10 to the 12th over 10 to the 13th will just leave 1 over 10. 12 of our 10s are being canceled and leaving 1 10 on the bottom there. Now we have e, a natural exponential function. We're going to cancel that by using the natural log. So natural log both sides. It's going to drop our exponent down. And on the left side, we're going to take the natural log of 1 over 10. That's a decimal value. The last step is to undo this division of 8,223 by multiplying both sides. We get approximately negative 18,934, but that is what negative t is. So the opposite of that would be positive 18,934. And we're talking about years is our t value. So this fossil is approximately 18,934 years old. So back on the front page, we saw that negative exponent telling us that we had a decay model. So carbon dating, or really radioactive decay, generally follows that exponential decay model. On to the next one. Magnitude of earthquakes. One way that we can use the common log. So reading through this information, we have 2 earthquakes happening, one in South Carolina and one in Japan. We're going to figure out the intensity of each earthquake by using this equation. R is representing the magnitude, or that value seen on the Richter scale. So in South Carolina, we had 4.1, so we'll substitute that into our R spot. Log base 10 of I over I sub 0, which we're told is going to be represented using 1. So really not necessary in our equation if we're dividing by 1. So I is going to represent the intensity. We're going to solve for I. So in order to undo log base 10, we're going to exponentiate. Put 10 base and raise everything into the exponential position. That's going to cancel our log on the right, leaving us with I. And so the intensity of the earthquake in South Carolina is going to be 10 to the 4.1. You could find that value if you wanted. We'll just leave it in this exponential form. Same thing with Japan, except that time the magnitude was 6.5. So we'll say R is 6.5. Again, we'll exponentiate, raise everything with a base of 10. And so the Japan earthquake is a 10 raised to the 6.5 intensity. If we compare the 2 intensities and figure out how much more intense the earthquake was in Japan, then we're comparing this Japan value to the South Carolina value. We're going to use a ratio to compare 2 values, which turns into division. If I'm dividing numbers that have exponents, I'm going to subtract their exponents. So 6.5 minus 4.1 is 2.4. So the difference in our intensities was 10 to the 2.4, which we could represent as approximately 251. And so the Japanese earthquake was approximately 251 times more intense than the one in South Carolina. So that was a natural log application. If we go back to that front page, that would be that last sort of graph or model. So magnitude of earthquakes represented by that. All right, a couple more. Another population growth, just slightly different, less complicated than that first one we did. This time we're given the population of a city is represented by this equation. P is going to represent the population, and T is going to represent the time in years after 2000. So when did the population reach 190,000? We're going to plug that into the P spot representing our population, and we're going to solve for T for the time at which it took to reach that population. So first we're going to undo that multiplication of 95,300, divide both sides. Next, we have the natural exponential function here, which we can undo by natural logging both sides. That's going to drop our exponent down on the right, and we have the natural log of that decimal value on the left. Last step, just divide by 0.055, and we use our calculator to get that decimal value that's approximately 12.5 years. So let's think about that in terms of the problem. It's 12.5 years after the year 2000, so we're going to reach that population of 190,000 sometime between 2012 and 2013. Another population growth, we already established what model that was. However, notice that when we solved for T, that was a natural log application. And so what you could do is talk about that 5th model right there, the natural log model. Generally, if we are solving for T, represented in an exponent position, we're using logs to solve for it. So either of these could represent the time it takes for something to grow exponentially. All right, one more. Let's talk about the spread of a virus. On a college campus of 5,000 students, we have a flu virus spreading, represented by this equation. T is going to be the number of days in which people are infected. Y, or the output, is going to represent the number of students who have the flu. So the first question, how many students are infected after 5 days? This is just the substitution problem. Plugging 5 into the t-spot and getting the output of the number of students infected. So plugging that into our calculator, we get approximately 54 students are infected after 5 days. A little bit more challenging problem. The college will cancel classes when 40% of the students are infected. So after how many days will the college cancel classes? So we're going to be solving for t, the number of days. And we need to know how many students 40% are. Well, in the school we had 5,000 students, so 40% of 5,000 is 2,000 students. So when 2,000 students are infected, the school closes. So let's figure out the time in which it takes to infect 2,000 people. First step, we are dividing by this quantity, so we're going to undo that by multiplying both sides. Since it's over on the left now, we need to undo our multiplication of 2,000. We're going to divide both sides by 2,000. So another way you could do this is cross multiply. So now we have the denominator here on the left side, and this 2,000 being divided on the right side. So 5,000 divided by 2,000 is 5 halves, or 2.5. We're going to subtract that 1 for our first step there. Then we're going to divide by 4,999. Getting some decimal values here on the right that we could approximate or keep in fraction form. Now we have another natural exponential function, which we're going to undo by using the natural log. So if we natural log both sides, that'll drop our exponent down, and we'll natural log this fraction, giving us another decimal value. Last step, divide by negative 0.8, and that gives us approximately 10 for the value of t, representing the number of days at which 2,000 students are infected. So if the flu goes unchecked, for approximately 10 days, the school is going to have to shut down. All right, so taking a look at that last function type and trying to match it with what was on our first page there. That's going to be this logistic growth model. And so that could be one way to represent the spread of a virus. All right, so there's a few ideas of how we can represent exponential and log functions in real-life applications. Good luck practicing and solving those types of equations.